All right, this is like the fourth take on Jordan Canonical form at this point, and oh boy, I think this is like at least an hour and a half down the drain. Oh boy, yeah, this stuff's not easy. I'm not gonna blame. Like I understand. Like this stuff isn't easy. I myself can't record a freaking video correctly, even though I have the freaking problem sitting right on my monitor right here, and I still say something absolutely boneheaded that makes me re-record these videos. Anyways, welcome back. We're on Jordan Canonical form. Hopefully I don't screw this up again. Please no. And so let's dive into it. What is Jordan Canonical form? Well, okay. Let's have this matrix A. And my matrix A is this matrix 2, negative 1, 0, 1, 0, 3, negative 1, 0, 0, 1, 1, 0, 0, negative 1, 0, 3. Okay. Now, what do I want to do? Well, okay, so if this matrix is nice, right, we can write it like this. A equals SDS inverse, right? We've done this before. Okay. Cool. But what if this matrix is not nice? Well, that's where Jordan Canonical form comes in. We can write every matrix as A is equal to SJS inverse, where S is a basis of generalized eigenvectors, all right? And J is a Jordan block diagonal matrix. Okay. And then S inverse is just an S inverted. Okay. So when in the world do I consider SJS inverse? Well, let's take a look here. So, all right. With the 4x4 matrix, they'll usually just give you the characteristic polynomial so you can find the eigenvalues really quickly. I think I'm going to start doing that in these videos just to save myself some freaking time, since I've just been making mistakes and doing these guys over and over again. So in this case, this is lambda minus 2 cubed and lambda minus 3. Okay, cool. So yeah, let's say this is the characteristic polynomial. It might not be, there might be like a sign difference here and there. It's just not talking about that. So let's say this is the characteristic polynomial. And so then we got lambda is equal to 2, 2, 2, 3. Or in other words, lambda is equal to 2 with multiplicity 3. And then I have the value 3 by itself. All right. So multiplicity just means how many times is this eigenvalue repeated. And so step 1, of course, was to find your eigenvalues. What is step 2? Okay. Well, always deal with those eigenvalues that aren't repeated. Because when you start seeing repeated eigenvalues, that's where you start running into problems, like sometimes. And so deal with the eigenvalues that aren't repeated. So find eigenvectors for not repeated lambdas. All right, and so in this case, well, it means lambda equals 3, okay. And, we do our thing. Subtract 3 from diagonal, negative 1, 0, 1, 0, 0, negative 1, 0, 0, 1, negative 2, 0, 0, negative 1, 0, 0, okay. My pen spazzed out here, or I spazzed out, didn't check. And, okay, yeah, cool. And then let's say V1 then. What works? This works. 1, 0, 0, 1. This works, right? Yeah. Okay. So there's my eigenvector for lambda equals 3. And what do I do? Well, you just deal with it normally, right? So even when we have SJS inverse, right? So let's say S is this green dude, and purple is this purple dudette, all right? And all right, what do you have? Okay, so lambda equals 3, right? You just do your thing normally, 1, 0, 0, 1, right? You put your eigenvector there, and then you put your associated eigenvalue in the diagonal, right? Okay, so everything so far so good, right? Everything is so far so good. All right, now you want to deal with the repeated lambdas. Okay, And so in our case, we only got one, or one unique lambda that's repeated, which is 2. All right, lambda equals 2. It's repeated. And what do I get? I get 0, negative 1, 0, 1, 0, 1, negative 1, 0. All right, and then 0, 1, negative 1, 0, and 0, negative 1, 0, 1. Okay, and yeah, this is right. This is a minus 2i, right? Is equal to this. All right, a minus lambda I. Lambda equals to 2. Okay, so we get this guy. And now what? When you have a repeated eigenvalue and you find a minus 2i, there are two important things we need to consider. We need to consider the multiplicity of lambda. In this case, it's 2, right? So in this case, it's 2. And this is equal to 3. Okay. What's the other thing you need to do? The other thing is that I need to consider the nullity of a minus 2i. I need to find what the nullity of a minus 2i is. And in this case, the nullity is going to be 2, right? Why is it 2? Well, it's because this row and this row are repeated, so one of them will cancel each other out, right? If you do row reduction, and then this row and this row are repeated, so yeah, they cancel out as well. Okay, so nullity is 2. Multiplicity of lambda is 3. What does this mean? Well, all right, so when you do this, right, when you consider the multiplicity and nullity of a minus 2i, you want to pull down this S matrix. You want to look at S matrix. And so let's pull down S, right? S. All right. I'm gonna put it more over to right. Okay. All right. So remember S. It was just 3 on the diagonal. Okay. Cool. So what does this mean? All right. Multiplicity of lambda is equal to 3. What does this mean? Well, that just tells you what the absolute largest block on the diagonal can be. So in this case, I can have a ginormous 3x3 block on the diagonal if all things go bad, if under certain circumstances, right? The largest block I can absolutely have is a 3x3 block on the diagonal. So that's what the multiplicity tells me, all right? So I can have a 3x3 block on a diagonal under certain circumstances. Okay, but now I have to deal with nullity equals 2, all right? And what does nullity equal 2 mean? The nullity equals 2 means that go to this 3x3 block right here, right? Go to this 3x3 block, and you need to split this 3x3 block up into 2 smaller blocks on the diagonal, okay? So how can I do that? Well, one way I can do that is I can say, let's see, I can take a 1x1 block here, right? And then I can take a 2x2 block down here, right? So that's one way I can split up the 3x3 block into two smaller blocks. All right. What's another way I can do it? Well, another way I can do it is I can split up, get a 2x2 block up here and a 1x1 one block on the bottom right, and that's also 2 blocks, right? So if this were 2 and this were 2 and the bottom one was 1x1, right? That's 2 blocks. Is there any other way? No, there's no other way to do it. It's a 2x2 block on top or 2x2 block on the bottom, and then you move the 1x1 block accordingly, right? So there's no other way to do it. And so, yeah, so I have a 2x2 block and a 1x1 block, and it has to be that way. And you know, order doesn't matter in this case, so let's just leave it like this, and I'm gonna write it down. So it's, I have a 2x2 block and I have a 1x1 block. Okay. Now what? Now we need to start raising matrices to powers, okay? And what power do I raise it to? Well, you take a look at your dimensions and you're like, oh, okay. Well, for one of them, I have to raise it to the sec squared. So let's deal with that one first, right? Let's square our matrix. So I have to take a minus 2i here. 0, negative 1, 0, 1. 0, 1, negative 1, 0. 0, 1, negative 1, 0. 0, negative 1, 0, 1. And then you got to multiply it by itself. Okay? So this guy again. Cool. Okay, and what do I get? Well, I get 0, negative 2, 1, 1. 0, 0, 0, 0, 0, 0, 0, 0. and 0, negative 2, 1, 1. Right? Okay. And now what? All right, so I squared it, right? This is a minus 2I squared. Okay. Well, now we got to deal with our S friend. All right, remember S up here? Oh, damn it. Okay. Purple is J, my bad. Purple is J. So this guy right here is J. Sorry, I called it S for the last 3 minutes. I really don't want to make another video, so just bear with me, right? J. Good thing I followed color convention, right? So purple is J. Now we have to consider the S matrix, right? And what is the S matrix? S matrix up here is 1, 0, 0, 1, right? So that's S. And so far we have 1, 0, 0, 1. Okay. But now, right? So I'm dealing with this 2 by 2 block, right? That's why I squared it. I squared it because I'm dealing with my 2 by 2 block. And so that means these next two vectors I'm going to find are going to correspond to this 2 by 2 block, right? So it's going to go here, and it's going to go here, right? It's going to go in the next two columns, correspond to the 2 by 2 block. And how do I find them? Well, this guy on the right, it's going to be a special vector. We're going to call it VG, okay? Bear with me for now. Call it VG. This vector here is going to be a minus 2I times VG. Okay? So, how do we find VG? Well, what did we just do? We squared a matrix for no apparent reason. And there is good reason that we square that matrix. It's because we have to use that matrix to find VG. So, VG satisfies the following. It satisfies a minus 2I squared is equal to 0, the 0 vector, times VG. Damn it. VG. All right. And it also satisfies a minus 2I times VG is not equal to 0. Is not the 0 vector. Why is it not the 0 vector? Well, take a look at S, right? You're putting a minus 2I VG into a column here, right? And what if your column was 0? You get a 0 column, but you have to invert S. You can't invert a matrix that has a column of zeros in it, right? So a minus 2I VG can't be 0. So, okay, so VG satisfies a minus 2I squared times VG is equal to 0, but a minus 2I VG is not 0. So let's write down a minus 2I another time, for the millionth time. Actually, for me, it's like I've actually written this matrix down like probably 30 times, but every other time was deleted besides these few. So here's a minus 2I. All right, so now I need to find a VG. So this is VG, right, and this is VG. Okay, so I need to find a VG that makes it the 0 vector. And then here, the same VG needs to be something that's not 0. So what makes the top guy 0, but not the bottom guy 0? Pause the video, think about it. This requires, again, eyeballing. And resume it when you feel ready. But I'm going to go on. I know what it is. And it is 0, let's say 0, 0, 1, negative 1. Okay, so 0, 0, 1, negative 1. This works, right? Yeah, because, okay, that's 0. Second row is 0, third row is 0. Fourth row is 1 minus 1, 0. Okay, cool. So 0 now, we put it down here. 0, 0, 1, negative 1. Okay, and what do I get? I get negative 1, negative 1, negative 1, negative 1. Cool. So this works, right? We found VG. VG is a generalized eigenvector. That's why I call it VG, V sub G, okay? The G stands for generalized. And so, what now? Well, okay, well, this guy happens to be a minus 2I times VG, eh? So that's you know, that's handy because it can just go here, right? So now I can just put negative 1, negative 1, negative 1, negative 1 up there, right? And I can put VG, right? VG goes there. And so now it's 0, 0, 1, negative 1. Okay? No problems, right? Good. So, there's something here that you really want to do. And it's staring you right in the face. And the urge, it's so tempting to go +1, +1, +1, +1. Don't do it! Don't do it! That's not, no. So, when we're dealing with Jordan canonical form, just for the sake of your sanity and your grade, and for the sake of me grading your homeworks and your quizzes and your exams, or your TA or your instructor, don't mess with the signs. Just leave these guys as negative ones. Just do it. It hurts. It's very, very painful to see 4 negative signs in a row and just be like, oh, just multiply by -1. Just don't mess with the signs, okay? Because if you actually make this a column of positive ones, you need to do one more change. You can probably figure it out. But if you just multiply these guys and make them all positive 1, it's gonna be wrong. Okay, it's gonna be wrong. So don't do it. Leave the signs as is when you're dealing with Jordan canonical form. You'll thank me later. All right. So, what do I do next? Well, okay. So VG, right? That corresponded to the 2x2 block. This 2 satisfied a minus 2i squared VG is equal to 0. So now I have to deal with the 1x1 block, right? And so here I had a minus 2i squared VG is equal to 0. So now to deal with the 1x1 block, so now it's the 1x1 block time, right? This was a 2x2 block. All right, now I have to deal with the 1x1 block. So now I have to take a minus 2i, raise it to the first power. That's itself, right? A minus 2i to the first power is itself, right? Okay. And now I need to find some VG that makes it equal to 0. Hey, wait a minute. I know what that is. That's just an eigenvector. Yeah, it's just an eigenvector. 1x1 blocks. 1x1 blocks correspond to an eigenvector. All right. So 1x1 block corresponds to an eigenvector. And this should have tipped you off because this 3 up here, it's technically sitting by itself in a 1x1 block, right? It is. That's a 1x1 block right here. This 3 is just chilling in a 1x1 block. So a 1x1 block corresponds to an eigenvector. So this isn't actually VG. This is actually like V2, right? Since we already had a V1. So now we write 0, -1, 0, 1. I need to calibrate my pen. 0, 1, -1, 0. Screen. Okay. 0, 1, -1, 0, 0, -1, 0, 1. Alright, so now I need to find V2, right? That gets me zeros, or just an eigenvector. But it's so tempting to just say, oh, I found it. Yeah, right? Because it actually works, right? -1, -1, -1, -1. This works. This guy right here is actually an eigenvector. This guy's actually an eigenvector. It just happens to also be a generalized eigenvector. There's a common misconception here. All eigenvectors are generalized eigenvectors. The other way around is not true. All right, the other way around is not true. Not all generalized eigenvectors are eigenvectors. But anyways, we diverge. You want to put -1, -1, -1, -1 in there. Don't. Because remember, what do we have to do with S? We have to invert it. We have to invert S. There's a nasty inverse sign on S right there. And so, yeah, like, no, because then it's not invertible, right? S is not invertible. Don't do it. You can't also do positive ones either. That also doesn't work. So you actually just have to find another eigenvector. And with practice, again, this will come easily. But pause the video if you don't want this spoiled. The other eigenvector is what works? 0, 1, 1, 1. Right? This works too. So, and this one's linearly independent from the other vectors. Okay, it is. Trust me. I have the worked out solution in front of me. And so now what? Oh, yeah, you just put 0, 1, 1, 1 here, right? And since it pretty much behaves like, and it is an eigenvector, it's behaving like an eigenvector, right? Yeah, just put the eigenvalue corresponding to it on the diagonal, right? So you just put a 2 here. Okay, cool. All right, now what? Now we have to deal with this block right here. This block. All right, fill up zeros everywhere else. All right. So what's true about this block? Okay. Here's the case. Everything below this diagonal, right, has to be 0. So this guy in the lower left-hand corner is 0. Okay, cool, makes sense. You know, J block diagonal. It's upper triangular. Okay. What else? Well, eigenvalues go on the diagonal, so that's not surprising, right? But immediately above the diagonal, you need to put a 1 inside the block. All right. So here, you need to put a 1. And you can kind of think of the 1 corresponding to a VG. It's technically not correct, but you need to put a 1 there. Okay. And now you're saying, aha, Ivan, you're dumb. You missed one. You need to put a 1 up here as well, because it's above an eigenvalue that is repeated that you had to square, and it's in a block. No, this guy up here is still 0 because it has to be inside the 2x2 block. Okay, so only that guy. I make a lot of mistakes, but this isn't one of them. So that's the only one that you have to put, and we're done. We're done. We've done it. We've successfully done Jordan canonical form. And so this is how you find S. This is how you find J. We're going to do another example. We're going to run it back, and it's going to be slightly different. The example is going to be just a tiny bit different. You'll see in a bit when you watch the other video. But hopefully this makes sense. 2x2 blocks, right? You have to do the whole VG thing for 2x2 blocks and larger. And then when you only have like a 1x1 block, 1x1 blocks just mean eigenvalues and eigenvectors in the normal sense. Okay? And so, next video, we're going to do another Jordan canonical form, and then it's on to taking the exponentials of these guys, which isn't that bad after you learn Jordan canonical form. There's a reason why this video is going to be like 23 freaking minutes long, because the stuff is hard. And this stuff has taken me personally many times to get it correct. And so hopefully this is a very helpful video for you guys. And I'll see you guys in the next video.